Oh, let me forward this to myself. No, this. Oh, I have this back. Okay, maybe we should start class. Can everyone hear me out there?
Yes.
Yes.
Yes? Okay, good. All right, so what I'd like to do is I'd like to sort of start out by sort of giving you the plans towards the end of the semester, just so that we're sort of clear on how we're going to finish up. I have graded the first set of exams from Wednesday, so those are done. And so I'm going to grade the ones from Friday over the next day or two. So I'm hoping to have exams available on Wednesday and beyond. So I will keep you posted on this. Okay, so that's how it's going in terms of the midterm exams. All right, so let's see, where are we at? So I believe we are currently on week 12 over here. So what I'd like to do is I'd like to go over when the particular homework assignments are due. Okay, so I'll actually mark this in using a marker here. Let's use the red. Okay, so this is homework assignment number 9 over here. Oops. Let me do that. Okay. So this is homework assignment number 9, right? And that's due this week, and it's due. I want to make sure I don't mess this up. So let me see if I can do this. So this is due on 11/11. So it's due actually this Wednesday. Okay. All right. So now this part here will be homework assignment number 10, and that's due on the 18th. Okay. And then we have homework assignment number 11. All right, and that's going to be due on the 25th, just before Thanksgiving. All right. And now here's kind of the tricky part. So I want to actually combine the last 4 sections together. I don't see a point in having a homework assignment with just one section. So all of these together this is going to be homework number 12. Okay. And that'll be due on the 8th of December. So I'll actually send an email out giving this in more specific detail. Okay, is there any like question about this so far? Okay. All right, then what I'm planning to do is, just for your sort of planning ahead, I'm going to drop the 2 lowest homework assignments. So I'm going to drop the 2 lowest homework scores. Okay. So it'll be easy for you to figure out your homework grade. You just take the top 10 scores that you have, add them together, and that'll be out of 100. Okay, is that clear? I think that's just the easiest way to do it. All right, now I realize that the final exam is very close to the end date of classes. So what I'll try to do is I'll try to schedule the reviews probably in the last 2 days of class, since it's so close, okay? So the final is on December 11th, 2020, okay? From 12 to 3 p.m. We're gonna have to do it online. I haven't decided whether it's open book or not yet. So I'm sort of thinking that through right now. So I'll give you more details about that. Okay. All right, any questions on this so far? Yes, no? Okay. So more details will be forthcoming, but I just wanted to give you an outline of what to expect for the next 3 weeks. Okay. All right, good. All right, so today we're going to revisit the issue of base change. So let me go back to the notes here. So we're going to look at what's called change of basis. So sometimes you actually have better choice of bases than others, depending on the situation. Okay, so let V, let's say, be a subspace of Rn, okay? And whenever we have a subspace of Rn, we have a basis. So with basis, I'm going to call it script B, and that's going to be V1, V2, up to Vt. Okay, so you have these vectors. Now, whenever I have a element of V, I can write it in terms of the basis. So I'll call it X. Suppose that's in the subspace, then I can write X in terms of this basis. So X will be equal to CV1 plus C2V2 plus CTV2, right? And now what we can do is we can pick off the coefficients, C1 up to CT, and those are the coordinates, okay? So X here is going to, with respect to B, is C1, C2, all the way up to CT. So remember, these are the coordinates. All right. Okay. So now let's say that we have a linear transformation. Okay. So now let T from V to W be a linear transformation. All right. And script C equals, let's say, W1, W2, let's say Wm, be a basis for W. Okay. All right, now if I take an element out of the basis for V, let's say Vj, then I could write it in terms of the W's. More generally speaking, if I take T of X, this is going to be what? Well, this is going to be T of C1 V1, C2 V2, plus CT Vt. Okay. Now T is a linear transformation, so this is going to be equal to C1 T on V1 plus C2 T on V2 plus CT T on Vt. Okay. All right, now let's say I write things with respect to the basis C for T of X. So if I write the T of X in terms of the coordinates with respect to the basis C, this is going to be C1 times TV1 with respect to the basis C plus C2 TV2 with respect to C plus CT TVT with respect to C. Okay, so I'm actually writing the coordinate of T of X relative to the basis for W. Okay, we can do that. And now what I can do is I can sort of put this in a matrix form. So this is the same as multiplying the matrix where the coordinate T of V1 gets put down the first column. And then we just put the columns of T of VT. So we put all the coordinates down the columns. And then I have C1, C2, up to CT here. Okay? But remember, C1 up to CT, that's actually the coordinate of X with respect to the basis B. Okay? So now I can rewrite this. I'm just going to write it really big. Sometimes, you know, if you write it bigger, you understand it better. Okay, so if you take T of V1 with respect to C here, T of V2 with respect to the basis C, T of Vt with respect to the basis C. These are all down the columns, and this is X with respect to B. Okay. All right, so this matrix M, so M is the matrix of the linear transformation T with respect to the basis B for V and script C for W. Okay, so let's kind of step back for a second. So I'm actually writing T of X in a matrix form. And the way we're going to denote this, okay, we have a different notation later on, but let's just not worry about that now. So the whole point is that we can express our linear transformation. How do I get rid of this thing? Let's try doing that. Okay, well, anyway, let me go back up to here. So we're expressing our linear transformation T from V to W. So we're actually taking an element out of the basis B, and then we're writing the coordinate with respect to C. And then we're just putting them down the columns. Okay, so this M here, it depends on the basis B, and it depends on the basis C too. So the V's are in the basis B, and then you take the image of the basis elements under the linear transformation, and then you write each one in terms of the basis C for W. Okay, is that clear what we're doing? We're going to do some examples, but I just want you to see the philosophy on how we're doing this.
I've got a question.
Yeah, go ahead. Can you speak up, please?
Yeah, sorry. Can you hear me?
Go ahead.
How do you get from C1, C2 to CT? How does that equal X with respect to B?
Oh, because it's a linear transformation, right? Because it's a linear transformation, when I take two vectors, T of V1 and V2, it's T of V1 plus T of V2. So
Okay.
here it's because T is between here and here, it's because T is a linear transformation. That's why we can do this.
Okay.
Okay, it's a definition of a linear transformation. Okay, other questions? All right, so it's actually, in some ways easier if we actually put this into practice. Okay, so let's do that. So let's do an example. Okay, 1. Okay. So T is a linear transformation from B to W. Okay. And the basis B is going to be D1 and D2. Okay. And the basis script C will be equal to B1 and B2. Okay. We'll just kind of label it that way. All right. Now, when I take this linear transformation, I have to tell you where the basis elements go to. So if I take T on D1, that's going to be 2B1 minus 3B2. Okay. And T on D2 is going to be equal to minus 4B1 plus 5B2. Okay. And so the problem is to find out. Okay, so we're just gonna do this in practice. Find out what this M is. Okay. So we just write the definition. So what is M? Well, we take the image on the elements here, and we take the coordinate with respect to C, and we put it down the column. And we do the same thing here. And we put it down the column. All right. Okay, so what's the coordinate of T of D1 with respect to the basis C? What should go down the first column?
Is it minus,
And-
or is it 2 and minus 3?
2 minus 3, right? That's the coordinate, right? Okay, what about the next one?
-4, 5.
Good. Okay, so it's not as hard as it is. You just have to keep, it's just bookkeeping. That's all you have to do. Just make sure that when you write things down, you understand like, oh yeah, you're just taking the coordinates, and then you just pick off the coefficients of the basis elements. Okay? Any questions? All right. Okay, so now we want to suppose that we have a linear transformation T, and right now we want V to be W. Okay, so it's a linear transformation which actually goes from V to V. Okay, this is a very special case. Now, when you have V and W being the same, in some ways you only need one basis, right? So we let script B to be equal to script C in that case. Okay, so the M here, and let's say B is equal to, again, V1, V2 up to V2. Okay, so now your M will just be T on V1 with respect to B now. Okay, so because V and W are the same, we can use the same basis. Okay, and then similarly, we can go down here T on VT with respect to B. Okay, and when we do this, we have a special notation for this. This special notation is T with respect to just the basis B. Okay, we don't need two bases, we just need one in this case, when V and W are the same. Okay, does this make sense? Okay, this will actually come up in application. All right, and in particular, so that's one point. So if I take T of X with respect to the basis B, this is this matrix M times the coordinate with respect to B. Okay, so when the two vector spaces are the same, or the two subspaces are the same, then we can use the same basis for T and W. All right, any questions on this? All right, so why is this important? Well, it's important because, certain bases give you matrices which are nicer. We've seen this already with the idea of diagonalization. So if I take a matrix and I look at, and it's diagonalizable, then if I take the eigenvectors, then they form the matrix which allows you to sort of transform A into a diagonal matrix. And so what that matrix is this sort of change of basis. And so what you're doing is, with respect to the eigenbasis, you represent your linear transformation as a diagonal matrix. And that's what this next result says. Okay, so here's sort of the big theorem of the day. So let A be similar to diagonal matrix. Okay, so that is A is equal to P D P inverse. Okay, so D is a diagonal matrix and P is a matrix which has the eigenvectors down the columns. Okay. All right, so let script B be a basis for Rn formed by the columns of P. Okay, so i.e. these are eigenvectors for A. Okay, we've seen this before. Now suppose T from Rn to Rn is the linear transformation given by T of x is equal to A times x. Okay, so suppose we have this linear transformation. So then, if I look at T with respect to this eigenbasis, then I get a certain matrix, right? So what matrix do you think we get?
A with respect to the eigenbase.
Eigenbasis, yeah. So if I take T with respect to the standard basis, the one consists of unit vectors, I just get A back. So if I change the basis to the eigenbasis, what matrix do you think we get?
P.
Do you think it's P or do you think it's D?
D.
P. All right. Okay, so the point is that if you change your basis, your matrix, which represents your linear transformation, could be much nicer. And that's what this theorem says. Okay, so if you take the standard basis like E1, E2 up to En, then T of that basis is A. Okay, so maybe I should write that down. So note, if S is equal to E1, E2 up to En. Okay, so this is a basis. Oh, what happened here? Yikes. Okay, let me kind of clean up a little bit. Okay, let's try this. Maybe I was trying to write too fast. So this is a basis, which is the standard basis. Okay, so this consists of the unit vectors. Then if I write out t with respect to the standard basis, it's just going to be a again. Okay, and you've seen that before because that's what you basically do to get your matrix A. You take t of E1, t of E2, t of En, and you put those down in columns. Okay. So here what we're doing is we're taking a different basis, and with a different basis, we get a different matrix. Okay, good. So why don't we justify this, and we'll do some examples afterwards. So I'll just say this is the proof. Okay. All right, so first of all, let's let P be the basis, sorry, the matrix with the eigenvectors down the columns. Okay. All right. So when I do this, then with that, when I write my x, so if I write P times the x with respect to this, then I just get x back again. Okay, so basically the idea is like if I take an x and if I write it in terms of my the coordinates, then what am I doing? I'm taking C1 times B1, C2 times B2, C. So remember this is C1 B1 plus C2 B2 plus Cn Bn. So I can write my x in terms of the eigenbasis, and then the coordinate x with respect to the eigenbasis is just C1, C2 up to Cn. Okay, so if I take P times XB, I just get x back. Okay. All right, so that's nice. And so I can just take the inverse the other side. So if I take x of b, this is going to be equal to P inverse on the vector x. Okay, so the coordinate is, we've seen this before. To get the coordinate, you just have to invert the matrix and then apply x to it. Okay. All right, so, okay, so now okay, so B is equal to B1, B2, up to Bn, okay? So I want to take T with respect to B, and I want to actually compute this out. Okay, now by definition, how do I compute T with respect to B? I just take the image of T under each of these basis elements and I write it with respect to that basis. So I'm going to take T on B1 with respect to B, T on B2 with respect to B, T on Bn with respect to B2. Okay, that's just the definition of what this is. Okay. All right, now we know what T is. So we know if I take T of x, this is going to be A times x. Okay, so I can just replace T of B1 by A times B1. Okay, so this is going to be equal to A of B1 with respect to B, put it down the column. A of B2 with respect to B, put it down the column. A of Bn with respect to B, and you just put it down the column. Okay? Now, okay, so what is A times B? Well, we can actually put this back inside of this equation over here. Okay, so we can substitute A times B1 in for X. And so I get P inverse times A times B1. Okay, so I get P inverse A times B1 over here. P inverse A times B2. P inverse A times Bn. Okay? All right. Now I can just pull the P inverse times A outside because it's in every single one. Okay,
You
so
wrote
this is,
P inverse A backwards.
oh yeah, I have to take the A out. Sorry about that. Okay, so yeah, let me erase this over here. Okay. All right, so that's good. And then we have this reversed, but that's okay. And then this one is just P, so this is going to be equal to P inverse A times P. And this should be a diagonal matrix too. So let's see. If I multiply it by P inverse on both sides, should have probably just done this here. Sorry, I should probably just replace this. So this should be yeah, I better just change that. Okay, so I want to put the inverse over here first. And then the P over here, then everything's okay. All right, good. So this is D. Okay. All right, so basically the idea is that with respect to the eigenbasis, then everything is good to go in terms of being able to write your linear transformation as a diagonal matrix. Okay, so let's do an example here. Again for time. Okay, so let's do this example. And then what I'll do is I'll review this on, I'll probably review this on Wednesday, and then we'll do more examples later on, okay? So let T be a linear transformation from R2 to R2, okay? And T of X is equal to A times X. And find a basis for T of B, let me say it this way. Okay, so find a basis script B for R2 such that T with respect to B is diagonal. Okay. All right, now I have to give you more information, obviously, where the A here is the matrix 4, -2, -1, and 3. Good. Okay, so what should we do in order to find this P? Anyone? What did the previous theorem say? Okay, let's go back and review the previous theorem. All right. So first of all, we don't know yet whether A is similar to a diagonal matrix. But if it is, what can we actually, what should we do to get B then? What should we look for? Anyone? Can people see the screen?
Yeah.
Sorry, maybe I can't hear you. Go ahead and speak up, please.
We can see the screen.
Okay, so what should you pick for script B then? What should it consist of?
P inverse.
Read the theorem. What should it consist of?
Eigenvectors of A.
Very good. All right, it's there. So this gives you a recipe. You're going to look for eigenvectors for A. So we have to compute the eigenvalues, compute the eigenvectors. Once we get the eigenvectors, that will be the B, and we can write T with respect to B in terms of a diagonal matrix. Okay? So that's what we have to do. All right, so let's go back to eigenvalues. Well, we look at A minus lambda I. That's 4 minus lambda, 3 minus lambda, minus 2 minus 1, right? So if I take the characteristic polynomial determinant A minus lambda I, remember this is PA lambda, what's that going to be? 4 minus lambda, 3 minus lambda. Okay, so it's minus 2 times minus 1. That's 2 with negative sign. Okay? All right, now we just do some arithmetic. So this is going to be what? 12 minus 7 lambda plus lambda squared minus 2. Okay? So that's going to be equal to lambda squared minus 7 lambda plus 10. Does this factor? Does it factor or not?
No. No.
No?
Or, well, you can use the quadratic equation.
Yeah, but
It-
then can you just factor it?
It factors.
Okay, so what is it?
Um,
What do you got?
Lambda minus 2, lambda minus 5.
Thank you. Very good. Okay, factors, right? What are the eigenvalues of A?
Two and 5.
Thank you. The eigenvalues are lambda equals 2, lambda equals 5. How do I find the eigenvectors? What should I do next? What should I look at? Anyone?
Find null of A minus both the eigen I. Like, so first one's 2, second one it will be 5.
Good. So let's do that. Okay, so let's say I take lambda is equal to 2. Very good. We're going to look at the null space of A minus 2i. So what does A minus 2i look like? Okay, so that's going to be, I'm just plugging in 2 to 2 right up here, right? So I get 2 minus 2 minus 1 and then a 1. Okay, that looks pretty good, right? Okay, so if I want to sort of reduce, if I want to find the null space of this, I can switch rows too. So minus 1, 1, 2 minus 2, if I want to do it. Doesn't matter. If I switch rows, I get the same solution, right? I get 2. You can see exactly what happens here. Minus 1, 1, 0, 0, 0. Right? Okay, so I mean, you just do the same thing. So the null space of A minus 2I is going to be equal to, well, you just make this one free, right? So minus x1 plus t is equal to 0. So that means x1 is equal to minus t. Okay, so that's going to be t. X1 is negative, so that's going to be minus 1, 1. Okay, that'll work. So t is a null. Okay, everybody okay with this?
Isn't x1 actually just positive t?
Yeah, so actually it should be, so let me see, let me make sure. So it's positive t, thank you. So this is not quite right. It should be positive. All right, so if you take the inner product of 1, 1 with the row, you get 0. Okay. Is everyone all right with that so far? Okay, let's do the next one. Lambda is equal to 5. So I'm going to take the null space of A minus 5 times I. Okay, so I need to plug in 5 to this, so I get minus 1. I have it in my notes here. Minus 1 minus 2. So let me just write it down over here. So A minus 5I is equal to minus 1 minus 2 minus 1 minus 2. Okay, so you can see what you do in terms of Gaussian elimination. Okay, so you get 0, 0 here, right? You just knock out the second row by just subtracting from the first. Okay. All right, so this is free. So this is free. So x2 is t here. And so minus x1 minus 2t is 0. X1 is equal to 2t. And sorry, minus x1 is equal to 2t. X1 is equal to minus 2t. Okay. So let's just write it out. X1, X2. That's going to be minus 2. I guess there's a t out here and there's a 1 right here. Okay, that looks okay, right? So the null space of A minus 5I is spanned by the vector minus 2, 1, such that t is a null. Okay. All right, good. So, so the basis B is what? I mean, there are lots of choices here, but we can just pick out. So what should we pick for like our first element of the basis? Anyone? We need it to be an eigenvector. So what eigenvector should we pick?
The first
There are
one.
lots of choices, but just pick one. Go ahead.
You just pick the first one, 1, 1.
1, 1. Okay. So we just take 1, 1. Okay. Which is the other one we should pick?
Minus 2, 1.
Good. All right. And then if I take my linear transformation t with respect to this basis, I should get a diagonal matrix. And what's that diagonal matrix going to be?
The eigenvalues.
Right? So where do I put the eigenvalues?
On the diagonal.
Okay. So which one comes first?
2.
2.
Good. And the next one will be the 5, right? Okay, does everyone see how we did this? So we checked, first, so let me just kind of recap what we did. Okay, so we have a linear transformation from R2 to R2, given by T of X is equal to some matrix times X. And the matrix here is 4 minus 2 minus 1, 3. All right. So if we want a basis for which this T of beta is diagonal, we have to make sure A is diagonalizable. Okay, so in order to check whether it's diagonalizable, we better find the eigenvalues and the eigenvectors. And so that's what we did. So we computed the characteristic polynomial here, PA of lambda, and we found the roots. And the roots are going to be 2 and 5. Right? And for each of those roots, we compute the eigenspaces. So for lambda equals 2, we got a basis for the eigenspace. We know how to do that using Gaussian elimination. For lambda equals 5, we got a basis for the eigenspace. Again, it's just one-dimensional. And then in order to get the basis, we just take the eigenvectors as our basis. Okay, so we pick one out from the eigenspace for A minus 2i, namely 1, 1 here. And then we pick the other one out from the eigenspace for lambda equals 5. So that gives a basis, two-dimensional, makes sense. And then once we have that basis, we can diagonalize the linear transformation, or we can write the linear transformation with respect to this eigenbasis. And when we do, we get a diagonal matrix where the eigenvalues are down the diagonal. Okay, any questions on this? We're just applying the previous step.
What was the point of finding the basis B when the answer doesn't use it?
What do you mean when the answer doesn't? Well, I just wanted to point out, all the elements within the theorem. So, if you stopped here, then you get full credit. But I just wanted to explain like the other connection with the linear transformation.
Okay.
All right.
So is the whole point of this to, because some calculations are easier to do on a diagonal?
Yes. So the thing is, when you have things written out in terms of certain bases, computations can be easier.
But then you would have to rebase it back to the original. to
No,
kind of
not
get the answer.
necessarily. I mean, if you have things with respect, so it's called a recoordinatization. Okay, so let me kind of give you the philosophy here, right? So normally, our way of thinking, okay, so I'm just drawing a picture here, okay? So let's say this is R3, right? So normally, and this happens a lot in applications too. So our standard way of thinking, let me write this in red pen here. Let me just switch colors. Let me switch it to blue. Okay, so our standard way of thinking is to use everything relative to the axes, the X, Y, Z axis, and use the unit vectors. But that's not always the best way to think about things. Sometimes it's better, like in three-dimensional space, you actually want to write vectors. It's kind of like polar coordinates versus like standard coordinates. Sometimes polar coordinates are better for various applications. So like in this case here, let me do green. Maybe you want to actually look at something where your frame of reference is with respect to this space is over here in the green. Okay, so a lot of times, what you may have is you may have a different coordinatization of the same space. And if you have a different coordinatization, sometimes that lends itself for certain purposes, whereas it's cumbersome to just use the coordinatization via the unit vectors. Does that answer your question?
Yeah. So this could be useful in like computer graphics.
Yes, exactly. I mean, that's exactly what the type of application you can use it for. Okay, other questions? All right, so next time, I'll actually review this at the beginning of next class, and we'll do a few more examples before moving on. So, so I know it's kind of difficult, for the first time to kind of get this. It took me a while to get this idea too. So I'd like to review it a little bit more before moving on. with a few more examples. And then we'll talk about complex eigenvectors towards the end of next class. Okay, great. So any other questions before we leave? Okay, we'll see you on Wednesday.